Form 7 Physics, Lesson number 6 Electromagnetic Effects. In this first part, we will be observing about the terms magnetic flux density, magnetic flux, and magnetic flux linkage. And also we will be observing about the equations F equals BQB sin theta, which is applicable for charged particles moving in a magnetic field. And also we will be understanding about the equation F equals BIL sin theta that can be applied to a conductor carrying a current in a magnetic field. Right, to start with, now we will first of all see what is a magnetic field. So when defining a magnetic field in our advanced level, we use the following terms. It's a region of space which will cause a magnetic pole or moving charged particle to feel a force. That region is called a magnetic field. So I hope you understood. It's a region of space which would cause a magnetic pole, that's simply a conductor, or a moving charged particle to experience a force. If that experiences a force, definitely there will be a magnetic field. Now magnetic field, of course, we don't see it by our normal eyes. So there should be a particular representation for a magnetic field to represent its direction, to represent its strength. So we use magnetic field lines to represent them. Then the magnetic field lines represent the direction of the magnetic field from north to south, and also it represents the strength of the magnetic field. You can see very close to the magnet, the magnetic field lines are closer. It means if I consider a unit area, there will be more magnetic field lines. But when it is further away from the magnet, you can see that magnetic field lines are separated. It means that the magnetic field strength is not very stronger. Right. Now, in the last figure, we observed diagrammically how we can explain about the strength. Now, we also need to know how numerically we can explain it. That, of course, we do like this. We will use a term called magnetic flux density. So it is also known as magnetic field strength and refers to the strength of magnetic field, as the name implies. Remember, it's a vector quantity and magnetic flux density is measured using Tesla. Now, how would you understand about magnetic flux density? Generally, the word term or the term density means in a considered unit area. So when it comes to magnetic flux density, we will be talking about in a unit area perpendicularly how many magnetic field lines are present. That we call magnetic flux density. In a unit area, the number of magnetic field lines present which are perpendicular to the unit area, that is what we call magnetic flux density. So it would be a standard form when we say a unit area. So if you know the area, you can multiply it by the area, then you would know how many magnetic field lines would be there in the considered region. That, of course, it's a different term. Now, magnetic flux density represents how many magnetic field lines are there in a unit area. It is represented by capital B. I hope you grab the most important things. You have to use the word perpendicular to unit area and magnetic flux lines. and you have to remember that it's a vector quantity, and you have to remember that the unit is Tesla, and the quantity is represented by the letter capital B. Now, what is magnetic flux? Earlier we learned about magnetic flux density. Now we will discuss about magnetic flux. Magnetic flux means, now earlier per unit area, now we are considering any given area. So if you know that per unit area the number of magnetic flux lines are B, then in a given area, when we multiply B by that given area, you would get the total number of magnetic flux lines. That is what we call magnetic flux. So however, that also we consider as a perpendicular component to the area that we are considering. So magnetic flux, it is the area, it is the number of magnetic field lines that are passing in a given area perpendicular to that. Unit of magnetic flux is Weber, and the symbol is Chi. Okay. Now I mentioned earlier about that perpendicular idea. So here you can see that magnetic flux lines are not perpendicular to the area that we are considering. It is having an angle vertically theta. So we have to resolute them. I hope you can remember in the previous videos we learned how to resolute. So we have to bend these magnetic field lines away from the theta angle. So it's sine. We can say B sine theta is the perpendicular component of magnetic flux lines to the given area. Then perpendicular component of magnetic flux lines, when we multiply it by area, we get magnetic flux. Right. Sometimes it's not just one single area, because when we have a coil of wire, then it is not having just one unit area, it has several different turns of the coil. So they each carry an area perpendicular to the magnetic field lines. That we call magnetic flux linkage with N turns, or we can even say flux linkage of a coil. So we learned that magnetic flux linkage is magnetic flux density multiplied by area. That is per one turn. So if there are N turns, you multiply it by N. Then we get magnetic flux linkage with N turns of a coil. Right. Now after learning about that magnetic field lines, flux linkage, magnetic flux density, we have to move on to the next part of this lesson, which we call Fleming's left hand rule. It is basically acting with three perpendicular fingers representing the direction of current, the magnetic field and the force. It is applicable for either a charged particle or a conductor carrying current which is placed in a magnetic field. So when a charged particle is moving, we know that there will be a current, or when a conductor is carrying current, there will be a current. But when we place them in a magnetic field, they will definitely experience a force perpendicular to both magnetic field and current. That is what Fleming said in his left hand rule. But however, remember, if the current is passing parallel to the magnetic field, or at least no component is there perpendicular to the magnetic field, then there will be no net force in the conductor. Right. Now we'll try to apply Fleming's left hand rule for these three figures. Just try part A. You just have your fingers ready and put them in the correct direction. The thumb, the first finger and the second finger. Now you can see in part A, the first finger just after the thumb, you had to point it towards right. Why? Because the magnetic field is from north to south always. So when you place that first finger towards right, then you need to know that the current finger must be into the screen. That means make sure your second finger, the middle finger, is kept into your screen. So the force will be the thumb, which will be downwards if you have kept the correct orientation. So that means in this wire, in this green wire, the force will be acting downwards. Now we'll look at this figure. First finger north to south, the second finger, middle finger, must be pointing upwards. Point it like that and see which direction the thumb is showing. I hope you have figured it out. The thumb is showing into the screen according to Fleming's left hand rule. Then there will be a force acting on this wire into the screen. But in part C, you can't direct your first finger and the second finger both in the same direction. Why? They must be perpendicularly kept. So it means at least no component even perpendicular to the magnetic field. Therefore this wire is parallel to the magnetic field, hence no force is acting on this wire. I hope you understood that one clearly. Right. Then the strength of electromagnetic forces. Now we learned that there is a force acting, but we never learned how to calculate the value of that force. So this equation gives us the idea of how to calculate the value of the force. For an example, now they say the force F on the wire which has a current I through it while it is in a magnetic field P, it is given by the equation F equal BIL sin theta. Why sin theta is because you know that when the current carrying wire is there in this format, we can't resolute it towards theta, then it would be parallel to the magnetic field. We have to resolute it away from theta so that it would be perpendicular to the magnetic field. As we are resoluting away from theta, we take L sin theta, the component of wire perpendicular to the magnetic field. Current is I, magnetic field strength is B, then you get the force value. If it is already perpendicular, then that theta value would be 90 degrees, so it simplifies to the equation F equals BIL. Right. Now we learned about the force. Is there any experiment that we can measure the force? Yes. You can clearly see the apparatus that were fixed to find that force. Now you have the idea that the power supply is giving a current in here and it is passing through an ammeter to measure the current passing through it, and the circuit is completed. And also now what will happen here is the current is passing, there is a magnet in here. That magnet would, the two magnets would cause a magnetic field. So the current carrying wire is perpendicular to the magnetic field. Hence the current carrying wire would experience an upward force according to Fleming's left hand rule. Last slides we learnt about that. But according to Newton's third law, you can see that this wire is firmly fixed. So according to Newton's third law, there will be an equal and opposite downward force acting on this magnet, U-shaped magnet. Due to that downward force, in this scale we see a reading. That reading is a mass reading. So it does not directly give us the force value. Then how can you convert a mass value to a force value? We use the famous equation W equals mg. Weight equals mass into gravitational field strength. So there weight is the force. Now here, with the aid of that equation, we will multiply this answer, this value, by 9.81 so that you would get the force. Then that's how we determine the strength of electromagnetic force in the laboratory. Right. Now force on moving charged particles. This of course you have to be very careful with this one. That is because it's not like just a force acting on a current carrying conductor. So always remember like this. If an electron is moving, make sure the current is opposite to the direction of electron movement. That you know. If a positive charge is moving, direction of the current and direction of the positive charge would be the movement of the positive charge would be the same. Now you can see the electron is moving towards this side. That means current must be towards left. So your second finger must be kept towards left. Then the magnetic field, that means your first finger must be pointed upwards. So at this situation you can see that the force would be pointing into the page. When it is here, it would be pointing also to the left. When it is here, it would be pointing out of the page. That means everywhere, regardless of the position of electron or the charged particle moving in a magnetic field, the force will always act towards a particular center that we call a centripetal force. Due to a centripetal force, we know that this charged particle would have a centripetal acceleration, and due to the centripetal acceleration, it would move in a circular motion. If these magnetic field lines are not not perpendicular, then we would take the component of that one perpendicular to the motion of electron or the charged particle. If it is already perpendicular, then theta value would be 90, hence the equation would simplify to BeV. Now we will see how this charged particle can move in a magnetic field. Now before we observe this one, we will try to understand about the forces that are acting. Now you can see that the negative charge particle is moving towards this side. Magnetic field is from north to south. Movement is from this side. According to Fleming's left hand rule, at here the force must be acting in the vertically upward direction. That will be equal to B E V O any charge Q. So it is bended upward, and this one is rotating in a circular motion. Because at different places the force would be always pointing towards the center. That is the idea that you should have about forces on particles that are moving in a magnetic field. So to get it simple, I'll again explain. If a charged particle is moving in a perpendicular magnetic field, the charged particle would always experience a force that is perpendicular to both direction of motion and magnetic field. This force is always acting towards a center, which we call centripetal force, causing centripetal acceleration of the charged particle, making it move in a circular motion. That is the full idea about forces on particles. Right. Now, as we learned that it is moving in a circular path, there are some further calculations we can go for. Which is, we understood that BQE is the force acting towards the center, but we know that centripetal force is also equal to mv squared over r. Hence we can rearrange that equation so that r will be equal to mv over bq. mv is mass into velocity. We know that that is momentum. So radius of the circular path of a charged particle moving will be equal to momentum divided by charge of the charged particle and magnetic field strength, magnetic flux density. This means that if a charged particle is moving faster, momentum would be greater. Momentum greater in the sense radius is greater, so they travel in a bigger circle. And also it says that if the mass is bigger, then also momentum is bigger, so radius would be bigger. So, but however, if we increase the strength of the field or charge, then the radius would be smaller as they are in the denominator, so they are inversely related. So the radius would get reduced and the circle would become smaller. So by looking at these things, in the future we will be observing about the charged particles, and we will try to identify about charges and masses of different particles. We will be able to use these equations to identify about them. Right. So that's the end of this part 1. I hope you understood. Have a good day.